Hello everyone. Welcome to this video presentation of our IEEE ICASSP paper entitled A Game of Snakes and GANs. My name is Siddharth Ashokan and I am from the Robert Bosch Center for Cyberphysical Systems at the Indian Institute of Science, Bangalore, India. My co-authors on this paper are Fatwir Sheikh Mohammed, who is currently at the University of Washington, Seattle, and Chandrasekhar Seelumantula from the Department of Electrical Engineering at the Indian Institute of Science, Bangalore. Before we begin with the specifics of the paper, let's start with a brief introduction to Generative Adversarial Networks, or GANs, a generative modeling framework that's gained a lot of popularity over the past decade. GANs are a neural network-based generative framework originally envisioned to transform noise to images. Since then, the quality of images generated by GANs has drastically improved. As an example, we consider images sampled from the Met Faces dataset. The dataset samples can be seen as coming from an underlying distribution PD. A min-max game ensues between the generator and discriminator to learn the data distribution. The generator network accepts high-dimensional noise as input, usually Gaussian or uniform distributed, and learns to transform it to a target sample following an output distribution PG. The discriminator network, in most common settings, is a two-class classifier. Its task is to differentiate between the real and generated samples and percolate this information back to the generator through appropriately defined loss functions. The generator is trained to minimize this chosen loss by creating samples that are continually harder to classify by the discriminator. The objective is to learn the optimal generator, one that creates samples that are indistinguishable from the reals, ultimately confusing the discriminator. This is an overview of our paper. We propose a novel alternative to training GANs, one wherein we have access to the optimal discriminator function. The proposed approach alternates between training the generator and evolving particles with a flow over the gradient field of the discriminator. The generator is then trained to mimic the flow of the particles. We demonstrate performance on 2D Gaussian learning and learning the latent space distribution of images. Let us now look at a background for GAN losses. GANs were originally envisioned as divergence minimizing, considering the Jensen-Shannon, Pearson chi-square or Kullback-Leibler divergences. However, their training instability gave rise to the family of integral probability metric or IPM GANs, wherein a distance metric is chosen for the discriminator to approximate. The choice of the IPM results in a corresponding constraint class that the discriminator is drawn from. Various popular GAN variants such as the Wasserstein GAN, Sobolev GAN, or Fisher GAN all fall within this category. For example, the Wasserstein or W GAN minimizes the Wasserstein or Earth movers distance between the real and fake distributions with a Lipschitz 1 constraint class on the discriminator. In Sobolev GANs, the authors consider discriminators with finite energy in their gradients. In practice, however, the Lipschitz constraint is challenging to implement, and the penalty is approximated by means of a gradient-based regularizer evaluated over points interpolated between the reals and the fakes. Subsequently, a plethora of variants such as WGAN GP, WGAN LP, WGAN ALP, etc. have been introduced to enforce some form of a gradient penalty to approximate the Lipschitz constraint. The table here summarizes various popular gradient regularized GANs present in the literature. One such gradient regularized formulation we consider in this paper is that of the radial basis function based RBF Coulomb GAN. In RBF Coulomb GANs, the optimal discriminator D star was shown to be the convolution with the Coulomb kernel psi, the generalization of the 3D charge potential in n-dimensional spaces. D star can be implemented by means of a radial basis function expansion, which allows us to compute the optimal discriminator and its gradient in closed form. We leverage the optimal discriminator in RBF Coulomb GANs to train a GAN generator. We consider a gradient flow wherein the points are evolved by means of an active contour snake algorithm, which has been popular in image processing. We show that the proposed approach achieves superior convergence behavior on 2D Gaussian learning tasks. On latent space image modeling tasks, we demonstrate performance on par with Wasserstein autoencoders or WAEs, while the model converges an order of magnitude faster. We now briefly introduce active contour models. Snakes are closed curves in 2D developed by Cass et al. In the 80s, aimed at delineating the boundary of objects and images. The snake optimization is one of energy minimization involving the snake's tension and rigidity controlled by the second and fourth order derivatives of the snake respectively. The convergence of the snake is controlled by the external energy, which in the case of boundary detection is the gradient field of the image. We adapt this algorithm to the gradient field of the GAN discriminator. Given a generator distribution PG and the optimal discriminator D star, we consider snake curves centered around each generator sample and evolve the snake on the external energy field induced by the gradient of D star. The snake updates can then be approximated by a linear system of equations involving the inverse of a matrix A that represents the second and fourth order finite differences between sequentially ordered snake points. This gives rise to the proposed SnakeGAN algorithm. First, given the generator output and the gradient field of the optimal RBF Coulomb GAN discriminator T star, we initialize snakes centered around the generated samples. A few sample curves are shown here. The snake curves are evolved for T steps based on the active contour update equation. We subsequently update the generator on a least squares lost between the initial and final locations of the centroids of those snakes. Unlike in classical GANs, the generator can be trained on pairwise correspondences between its output and the target. The updated generator distribution would then mimic the distribution of the converged snake points. We trained SnakeGANs in 2D Gaussian learning tasks and observed superior performance compared to baseline GAN variants. The performance improvement is paired with reduced computational load, as we observed that the discriminator gradient field needs to be computed only once every 10 generator updates. The snake is represented as an ordered set of points distributed about the generated samples. The ordering of points facilitates accurate estimation of the second and fourth derivatives of the snake. We also consider a variant of the SnakeGAN with unordered points, randomly drawn from the generator distribution itself. Training this unordered SnakeGAN, we observe that the ordering of the points can be traded off for training stability. The unordered variant is scalable beyond 2 dimensions, but is susceptible to points diverging if multiple snake updates are employed, as observable from the trajectories presented here. The unordered SnakeGAN approach, denoted by SnakeGAN UO, achieves FID scores on par with WAEs when trained on the latent space representation of images, considering the MNIST, SVHN, and Celebi datasets. To summarize, in our paper, we established fundamental connections between GANs and active contour flow-based models. The SnakeGAN algorithm outperforms baseline GANs on Gaussian and latent space image learning tasks. The source code for implementing SnakeGANs can be accessed by scanning the QR code here. As part of our future scope, we will explore extensions of SnakeGAN in generating high-resolution images, leveraging results from diffusion and normalizing flow models. While we consider the basic active contour framework, variants such as GBF snakes or ballooning snakes could also be leveraged to improve the discriminator's gradient field. These are the key references cited across this talk. And with that, I'd like to thank you all for your attention and conclude my talk.